Okay, I think it's time to get started. Thanks all for coming. The first JINA Pizza Talk of the year, and our speaker is Dennis Muecher, maybe, from the University of Guelph. So Dennis did his PhD at the University of Cologne in Germany in 2009. And after a short visit as a medical physicist at the hospital, he moved to Munich and stayed there for 5 years as a postdoc and staff scientist. And since now 2016, he's at Guelph as an assistant professor. So he'll tell us all about his reaction studies for nuclear astrophysics. Please.
Thank you very much, Agnes.
Yeah, thank you very much for having me here. This is really exciting. So for those who do not know where Guelph is, it's just a 4 hours drive from here, just across the border, close to Toronto. And I have a joint position with TRIUMF, which is Canada's major lab for particle and nuclear and also medical physics. And as you know, Vancouver is, TRIUMF in Vancouver, that's pretty far away from this area. That's a 5 hours flight, and this is only a 4 hours drive. So it's actually much easier to get here than getting to Vancouver. So I'm very happy to be here. At TRIUMF, we have a 500 MeV cyclotron accelerator. It delivers 500 MeV protons for various experiments. You can do experiments directly with those protons, or you can produce secondary beams, very similar to how it's done here. It's a little bit different, I'll talk about that, but the general idea is the same to NSCL. So you have a secondary beam generated from a particle accelerator. And then we have different detectors here to do our measurements. Okay, I would like to encourage everyone to ask questions. I really like that. I ask questions all the time myself when other people are talking. So please interrupt me at any time. And it's really great if this ends up being more like a discussion and you give some feedback on the ideas I'm presenting here. That would be really appreciated. So fire off any questions anytime. Okay, I would like to motivate this talk about reaction studies in nuclear astrophysics with this slide here. I mean, these are very exciting times for everyone in our community, for nuclear astrophysics in general, because of the detection of gravitational waves. I mean, that's a phenomenal breakthrough. And it gives a lot of additional momentum to our field, because there's now so much new information, not only for the astronomers, but also for the nuclear physicists and the nuclear astrophysicists. And I think this plot here demonstrates that very nicely. What is plotted here is the so-called tidal deformability of a neutron star merger. You know that gravitational waves have been detected because neutron stars are spiraling and then merging. And one important parameter is this tidal deformability. I will not go into the detail what that is. Just in simple terms, it is a kind of stiffness of the neutron matter. And this is correlated to the radius of the neutron star. The radius of the neutron star is a very important parameter if you want to understand how neutron stars can merge and what elements are produced and so on. And those are correlated in the sense that a more stiff neutron matter gives you like a different radius for the neutron star. But on the other hand, this is also correlated, and that's plotted down here, to the radius of the 208 lead nucleus, which is such a tiny object. So those are femtometers, and those are kilometers. So it's amazing that this is connected, and it is connected because the same equation of state is describing both these systems. That means if we learn something about nuclear matter, and it doesn't even have to be very neutron-rich or exotic matter, we always also learn something about neutron stars and how they collide and how they produce the elements that we nowadays can find on Earth. But of course, there's more to nuclear astrophysics than just neutron star mergers and tidal deformability. You know that the elements that we find today on Earth, they are created in stars. In the initial burning phases, they are fused like up to iron. And then after that, it becomes a bit more complicated. There is the so-called S process. Is everyone familiar with the S process and the R process in this audience? Everyone Yes, good. It's always hard to judge what the exact audience is. If there's any young students who have never heard about the S process, please raise your hand and we can quickly explain it. So you know all that. So we have neutron capture going on in the S process. And then to produce the more neutron-rich stable isotopes, we need the r-proce, or the rapid neutron capture process. And of course, all those reaction rates and how and where that actually happens, that depends on nuclear physics. Right? So important input to understand this network of calculations involved here are mass measurements to get Q values. We need decay experiments to get the half-life of the elements which are involved, especially in the R process. But also reaction studies are very important, and that's what this talk is going to focus on. So reaction, of course, they give you reaction rates. So it is sometimes very hard to do the exact same reaction that happens in a star. Say, measure a direct P gamma reaction rate is sometimes very tough because the cross sections are very small at the temperature where it actually happens in the star. But we can get close and then we can extrapolate. So we would use indirect approaches in case we cannot measure the reaction rate directly. So that is sometimes something we do. But also structure studies are important here. You see indicated here already the shell closures in nuclei, and as you know, the shell structure influences the way the R process evolves here in a major way. So our strategy, I think, in our community, in the nuclear physics community, is we have to measure key data wherever we can. So we have to go to those nuclei which really impact our understanding of nucleosynthesis. And everything else, then we have to improve models and make predictions as good as we can in case we cannot measure it, right? And I will talk about both these aspects in my talk today. So TRIUMF, as I said, is our major research lab. This is a nice picture, but you actually don't learn much from that picture, but it's very nice to look at it. So this is where the proton beam is coming into the so-called ISAC hall, and ISAC is where we have all our equipment to do our experiments. I will zoom into this layout a little later. So this is a picture of our high purity germanium array, TIGRESS, somewhat similar to Gratina. So it's there to detect gamma rays with the highest possible resolution. So to start with, what is actually a direct reaction, and what's the difference to a not direct reaction? So a direct reaction works like this. You have some incoming beam, and this example here I've chosen 21 neon as the incoming beam, and then you shoot that on a target. In this case, it's a deuteron target, so we have a proton and a neutron there. And one reaction that we use a lot is the one neutron transfer reaction. What happens there is that the neutron, indicated in red, that is transferred to 21 neon, so you end up having 22 neon, and then you're left with a proton, which is our recoil, and that just hopefully, if we are lucky, hits our detectors so that we learn something about that reaction. So that is a direct reaction. It means that there is no fusion going on between the beam and the target. It's a direct reaction, so this particle is put into a certain orbit in 21 neon. So this is a process which goes very fast, and there is no complicated fusion going on between the two. The great thing about a direct reaction is that we can understand the kinematics. So we know the beam of, we know the energy of the beam, and the target is usually at rest. So we know the energies before, and we can also measure the energies of all the systems and also the angles after the collision. And then we can just use, in this case, two-body kinematics to learn everything about the reaction. If you have a fusion, then that doesn't work anymore, because once they start to fuse, you can't see anymore what happens inside, and then the system may evaporate something complicated, and then it's very difficult to reconstruct what has happened. So one step further, if you want to do an experiment, we need a target. This is a blown up CD2 target. That's usually just like 10 micrometers thin, but I made it a little bit thicker so you can see it. And so here's our neon beam. That arrives at a certain energy, and Ex here stands for the excitation energy. So it would be in its ground state usually. It's not excited. It's in its lowest possible state, and it hits the target, and it gets transferred into 22 neon, and it emits a proton, which is then detected here in that silicon strip detector, which measures the energy, but it also measures the angle of that proton. So what is important for the remaining targets to understand this kind of plot here? What I plot here is the proton angle in MEV, versus the proton energy in MeV. So say if the proton angle here is, this would be probably like 70 degrees or so, and this would correspond to a certain proton energy because this is just two-body kinematics, right? Everything is set, right? You know where the 22 neon goes to. You can also calculate that angle and that energy, and everything is fixed in stone if you know what the excitation energy is. So if the excitation energy, the final one, is also 0, right, also the ground state, that would be this blue line here, because then there is more energy left for the proton. If you want to allow for some excitation here of the 22 neon, then you will have, at the same angle, less energy left, because the energy for the excitation has to come from somewhere. So the proton will have less energy at the same angle. So an excited state would be this orange colored line here. That would correspond to an excitation energy of 2 MeV, and you can go higher. The gray line here would correspond to 5 MeV. So that's basically what you can measure, because you can measure the proton angle and you can measure the proton energy with a silicon strip detector, and then you get exactly this kind of plot. The good thing is you see now here the excited states in your 22 neon nucleus. You see the ground state, but you also see the excited states. So you can identify them, you can measure the energies, but you can measure more about them. We'll talk about that later. In addition to that, if you do not only want to use silicons, we can place a germanium detector here to measure the gamma rays which are emitted in case we have an excited state which emits gamma rays, right? Is that roughly clear? Is there any questions, please? No questions? That's a very good question. So that, of course, depends on the thickness of the detector. A typical silicon detector is about 300 micrometers thick. And that would stop roughly something, I would guess, around maybe 10 MeV or so. So what we usually do is we have actually 2 layers of silicon. The first silicon layer is very finely pixelized, and the particle actually punches through that. And then the second layer is a thicker detector. We call it a pad detector. We usually go for 1 millimeter, but you can also buy 2 millimeter. That brings you up to maybe, I would have to guess, but maybe 20, 30 MeV or so. Also depends on the angle, of course, say at 90 degrees. Beyond that, you have punched through both layers. Then you can still reconstruct the total energy, because you have energy loss and energy loss. And that will depend on the total energy. So you, by simulation or calculation, you can get back the total energy, but your resolution will not be as good. So a thicker detector is better there. Yeah. We have more questions there. Oh, sorry, proton angle and MeV. That's a terrible mistake. Thank you. There you go. That's just in degree in lab. This is just a 0 degree and 180 degree up to here. Sorry for that. Yep, that would be, I don't know how to calculate from MeV to angle. Yeah, more questions to the slide. It's an important slide, and if you're new to the concept, it's not easy to get it. But the good thing about the direct reaction is that you can reconstruct the kinematics so that you have this information. In a fusion reaction, it doesn't really work that way anymore, and you don't get these kinematic lines so easily. So this is what is nice about a direct reaction. So if you now see these lines, I guess you can kind of reconstruct that this is a state. So if you know the kinematics, you can like project all this so that it always belongs to the same excitation energy. So you can make this a one-dimensional plot and get rid of the angle. So then only plotting the excitation energy, that would look like this. That's for a different case, but it's a nice plot to show the example. This would here then be the peak for the ground state transition, and there would be a second peak, which would correspond to another band, and so on, right? You get the idea. You can reconstruct the excitation energies from such a simple measurement. Okay, so why do we, so what is an example? How can we use that for nuclear astrophysics? I have chosen 21 neon DP for a specific reason, because we have just done an experiment with that at TRIUMF, which is related to nuclear astrophysics, and it's related to this chain of reactions here. This is a typical chain of fusion reactions going on in an HPGe stars at late burning stages. You produce 18 oxygen. We'll skip the details how to get there, but it is produced in significant amounts. And now here is a branch which is very important to understand. 18 oxygen can either undergo an alpha capture into 22 neon, or it proceeds here with a p-alpha reaction to produce fluoride. So there's a couple of things interesting here. Two of them are, first of all, we don't really understand where the fluoride is coming from in the universe. There is a long-standing discrepancy for the amount of fluoride in the universe. There's like a disagreement between the calculation and observation, and that always points you into something which is not fully understood. So this might actually be related then to this branch. So if you don't understand how much of the oxygen 18 goes this way over this way, then you have a difficulties understanding fluoride 19. So that's one reason why it's interesting. The other reason is once you have 22 neon in your star, you will do an alpha N reaction with quite high probability, forming 25 magnesium. And it turns out that this neutron here is one of the major sources for the neutrons in explosive nucleosynthesis, especially in the S process. So a lot of the neutrons in the S process come from this reaction here. So if you better understand how much 22 neon we have, you also better understand like an important input for the S process calculations here. So we were interested in this reaction here, the alpha gamma oxygen 18 going into 22 neon. So this is one of the examples where we would like to measure directly, but it's very hard to do because the cross-section is very low. So first of all, what's the impact anyway? Here's a paper. They recommended new values for this alpha N reaction from 22 neon into magnesium, but they also recommended a new alpha gamma on 22 neon. And the change that this has on the abundance distributions for any element, or like mass 100, is shown in this graph. So shown here is the difference to what was expected before to what came out of the new calculation. This is a log scale. So you see, for instance, that by changing the theoretical prediction for these capture rates, that the magnesium is now produced here with a factor of something like almost a factor of 10 less compared to before. But so that's quite obvious because they changed that reaction rate. But it actually has an impact on this entire chart, like molybdenum-92 is now underproduced with a factor of 8 compared to before, just because of changing these reaction rates. So just by understanding one reaction and one key reaction, you get a completely different prediction for this entire network calculation. So this is why it's important to go to the key reaction and measure that and understand that as good as possible. So we thought that this is one of them. You can actually measure this reaction rate directly if you are a certain amount above the threshold at which this reaction takes place. You know, there is a certain minimum energy that you need so that this reaction can take place. We say this is our resonance energy 0. And then above that, you start to populate 22 neon through this alpha gamma reaction. But if you are just above the threshold, then measuring that in the laboratory is very difficult because the cross-section is still very small. Just if you go above a certain minimum threshold, you start to be able to measure that directly in the lab. We could use that, for instance, at TRIUMF. We could do that at TRIUMF using the Dragon device, which is like a recoil separator, and you can measure this reaction rate directly. It becomes clear in this plot. This is here the resonance energies in 22 neon. So I said, so at 0, the reaction just energetically becomes possible. The first known resonance, the first known state in 22 neon is just like 60 keV above that threshold. That is very important. However, the cross-section in the lab is like something 10 to the minus 40. That's not really the cross-section. It's called the resonance strength. But it indicates that it's very hard to populate that in experiment, because it is just energetically, it's just allowed. But the cross-section due to that is very small. So what you can measure in the lab is something which has a resonance strength in the order of 1 in these units shown here. So you are like 40 orders of magnitude below what you can do. So there's no way you can ever measure that, right? 1 is already like a fancy device at a facility like TRIUMF and a week of beam time and a group of scientists involved. Then you can measure a resonance strength of 1 microeVol. But if you want to do 10 to the minus 40, that doesn't work directly, right? And this scales very sharp with the energy. Once you go away from that point where the reaction is just starting to be possible, then your resonance strength can ramp up quite dramatically. So the uncertainties in the reaction rate is shown here. This is, again, the resonance strength, and this is the temperature here. So for instance, these 219 kV resonance is still uncertain by a factor of 10. No, this is a log scale with 5 orders of magnitude between here and here, right? So this is like a factor of 10. And the uncertainty comes because the spin of the resonance is unknown. This is the major input, right? If you don't know the spin and you don't know exactly how much angular momentum is involved in creating this and populating this state, and you have to measure that in order to get this error bars down. And that was our idea, to measure that. So we said, okay, we can't measure that directly because we are, in this case, 12 orders of magnitude off. But we can measure the spin and then put that into our calculations. And that already brings it down from a factor of 10 to maybe a factor of 2. It's not a direct measurement. It's an indirect measurement, but it has a significant impact on our understanding. And this is what we can do now with the direct reaction. So yeah, here is a little bit a better overview about this ISAC facility where this experiment took place. The beam is coming from here in case it is a secondary beam. There's also the possibility to do stable beams at ISAC. So if you have a great idea for a stable beam experiment and you can't do it here for whatever reason, TRIUMF also has that possibility. And then we have a bunch of low energy experiments going on in ISAC 1. This is Dragon, I mentioned that before. This is for direct measurements of nuclear astrophysical reaction rates. There's also TUDA, which is also designed for nuclear astrophysics. Everything here is up to roughly 2 MeV per nucleon or so. If you want higher beam energies, there is a pulse accelerator, which is this beast here. And that brings us into the ISAC 2 hall. That's our high energy hall, high energy TRIUMF standards. So this is up to 10 MeV per nucleon. And we deliver that, for instance, to our TIGRESS array. That's where our high purity germanium detector sits. And that's where we did this experiment on 22 neon. So the way it works is that the beam would come into our array and it hits our deuterated target. So what we do is we start with the 21 neon beam, as indicated before, and shoot that on deuterons to populate 22 neon. So that's not the reaction which actually happens in the nuclear astrophysics environment, but it does populate 22 neon. And we just learned that we then see all these excited states and that we can also get the spins of those excited states, right? That's the indirect approach. So we have silicon detectors, it's called SHARC, surrounding the deuterated target to detect the protons. And we also have TIGRESS detectors to detect the gamma rays here. And as mentioned before, we can reconstruct the kinematics, so we get the excitation energies back. This is plotted here. This is the excitation energy. This time it's the correct unit. It's an MeV. And this is just the counts. And the ground state will be somewhere here. Excuse me. And then you see all these states popping up in 22 neon. But you see it's pretty dirty, right? There's not really much you can see from that because we haven't made use yet of the gamma rays in this experiment. Is this roughly clear? Any questions on this slide? I think clear. Okay, so what we now want to do is we want to clean this up because we want to identify the resonances of interest. To remind you, they are at high excitation energies like 10 MeV or so. So that's where we would like to measure. So this matrix here now shows the measurement of gamma ray energy versus the excitation energy. Everything is so this is in MeV, this is in kV. So what happens here is you excite a state at a certain excitation, and then it will rain down with gamma rays. It can decay back directly into the ground state, or it can like emit a cascade of gamma rays. So say if you have a 10 MeV state over here, then there could be a 10 MeV gamma ray. So this blob here would be a ground state transition. If you have something here, that would mean that a 10 MeV state decays with like a 5 MeV gamma ray to a lower lying state, right? So this is like this entire level scheme that you can measure. And now we can gate in this matrix to clean up things. For instance, you can now gate on a gamma ray. So you can make like a one-dimensional projection of these excitations by gating on one gamma ray energy. And then you nicely see, instead of having all this complicated spectrum here, you only see one resonance, in this case, around 9 MeV excitation energy. and it's basically background free, right? So this is what you get from the silicon detectors, but this time we make use of the germanium detectors to clean it up. You can also make it the other way around. You can gate on, say, a 9 MeV resonance, and then you can get the gamma ray spectrum back, which is shown here. So this, for instance, is the decay of the 9.85 MeV resonance. If I go a little bit back here, that is exactly this resonance here with unknown spin. And it's actually one of the most important ones at low energies, which cannot be measured directly. So we populated it, and we see its gamma ray decay. That's this line here. That's this single escape peak, and that's this Compton background here. So we have a nice clean spectrum. This experiment took just place in October or November last year at TRIUMF. So this is like online quality data. It's going to be hopefully a lot better than that even. But we have very good statistics, and this will allow us to measure the spin. There's two ways we can do that. We can either look into the angular distribution of the gamma rays, basically measuring if that's, for instance, an E1 or an E2 gamma ray. Or we can also look into, so that would be this one. Or you can also look into the so-called angular distribution of the particles. So you look how many protons go into which direction, and that also points you towards the spin of the states. So we have two ways at the same time to analyze the spin. We can use the gamma rays, or we can use the particles. And hopefully they will lead to the same result. But it's always good to have a cross-check for this, right? Yeah, and then, so the goal is then to get the spins and dramatically reduce the error bars for this key reaction rate. So that was a run through like an indirect approach to contribute with a direct nuclear reaction to nuclear astrophysics. Are there questions to that? There's a question. Yeah. So this is those are the excited states in 22 neon. So let me go back to, so the experiment we're actually doing is this one. So 21 neon is in its ground state, 22 neon is now excited, and it can be excited at like 10 MeV or something. That's that second row shown there. So that's the excitation energy in 22 neon. Now, if you subtract from that the energy that you need to do the alpha gamma, like this thing here, then you end up with what we call like the resonance energy, right? But it refers to the nuclear state at around 10 MeV excitation energy. More question, yeah. Yeah, that's always a critical thing. So particularly in this case, say you have a 10 MeV state, the gamma ray energies can be very high. And as you know, detection of high gamma rays is very unlikely because they mostly do Compton scattering. You need a very large high purity germanium detector to actually absorb them and get like a full energy peak. And the efficiency of that is at best case just a few %. And then in addition, you have the silicons. Silicons do better because whenever a charged particle hits the silicon, it always gives a signal. So that's literally almost 100%. However, we do not cover 100% of the 4 pi. So, but say 50% or so, I would say we have for the silicons. The germanium is the critical thing. So it would be nice to only use the silicons, but that's not possible because this is a spectrum where we really can't learn anything for that high excitation energies, right? There is different approaches, but that was our approach, and it works quite nicely for this case. Yeah. More questions? Yes. Yes. How do you get the spin? No, they're not unbound. They're bound. Yeah. Yes, sure, yeah. Mm-hmm. Yes. Yes, exactly. That's what we want to do. I think this is what you're referring to is basically this plot here. This is the relative intensity of the particles as a function of angle, right? Now, if it's overlapping with other resonances, then you have to like unfold this. But if you gate on gamma ray energies, it's usually clean enough. So you only have one resonance, like this guy here is pretty clean. And you can just plot its intensity as a function of angle. And that gives you the spin. Or it gives you the L transfer. It doesn't give you precisely the spin, but it tells you how much angular momentum has been transferred, and you can relate that to spin. Yeah, was that your question? Sort of. Okay, we'll discuss it later. Okay, more questions? Okay, if that is not the case, so that was a light nucleus. I think my title indicated I want to talk about heavy nuclei, so let me start doing that now. How do I do time-wise? Okay, good. Okay. So I wanted to address two more topics. One is the importance of shell structure. I mentioned that in my introduction. You see all these magic shells here, and we know that also nuclear reaction rates behave a lot different under the influence of shell structure. I like always to show this example here. This is the neutron capture rate in barns. So that's the possibility that you capture thermal neutron or whatever. Actually, the energies should be plotted here. It's not important. So it's the capture rate probability on 197 gold and lead 208. And the details, these resonances are not so important. What is important, there's 5 orders of magnitude difference here. That's a lot. And the basic reason is that 208 lead is a doubly magic nucleus. It has a low level density and so on, and a low Q value for neutron capture, whereas 197 gold is a more deformed nucleus with a higher level density. And so this demonstrates to you that shell structure is very critically important if you want to, for instance, understand neutron capture rates, which of course are important for the r-proce and the s-proce. There's actually still many things we don't understand in this heavy region. I always like to point towards this Nature article here. Those researchers measured the abundance of 244 polonium in deep sea reservoirs and extracted from that how much of this transactinides were produced in the universe, and they compare that to what they would actually expect to be produced in the r-proce. And you see this is what they measured in the crust there on Earth. This is with accelerated mass spectroscopy, and they compare that to the network calculations from the r-proce, and there's 2 orders of magnitude difference. There should be 100 times more 244 plutonium than you actually find on Earth. So it really means we don't understand everything yet. That, of course, has to deal with the fact that the r-proce in this heavy mass region involves very neutron-rich nuclei, which maybe even at FRIB we are not all be able to produce and study. So I think we really rely on a good understanding of things like nuclear shell models. And so like the question, is the N equals 126 neutron shell still a good neutron shell for the r-proce or not? It can gives you many orders of magnitude differences in neutron captures. I will keep that very brief and simple. I wanted to point out that shell evolution still is an open problem. I think Alex would probably agree to that statement. It's very hard to understand what actually makes what actually changes the shell model if you go neutron rich. I want to break it down to 2 contributions. One is the so-called tensor force. Probably everyone here knows that the strong force is a tensor force. So it's the orbital motion and the spin motion, which are coupled in a complicated way. So if you change the isospin of your nucleus, if you go like neutron rich, then this tensor force has some effect. The other thing which may change shell structure is the fact if you go neutron rich, then your nucleus starts to become a halo nucleus. You may have heard from like lithium-11 as a halo nucleus. Something similar may also happen in heavier nuclei. It can, for instance, explain the so-called island of inversion, where N equals 16 becomes a new shell closure and N equals 20 disappears. Basically, what happens is that if you go neutron-rich, these halo nuclei, these halo orbits, they extend further out in their radius. They become softer, and that changes the energy as a function of which orbital is involved. And that also can explain shell evolution. It's very hard to disentangle the two. In experiment, that always looks very similar, but it's very important to understand what is actually causing it, because otherwise you can't make any predictions really far outside of stability. So the approach here is to make fundamental studies. So one of the things we recently tried is the following. It's again a direct reaction, a transfer reaction. This time we transfer 2 neutrons from a tritium target to 28 magnesium, which is unstable. Now the idea is if you have the final 30 magnesium nucleus, and that is already neutron-rich, if that is a halo nucleus, you would see an enhanced transfer into 30 magnesium because it's easier to catch these 2 neutrons if the wave function extends further out. So it has been shown in this paper. I forgot to put the reference, sorry for that. Ask me if you're interested. This is from Lenske and Schrieder et al. Plotted here is the cross-section of this direct reaction as a function of this time the beam energy in MeV per nucleon. And you see if you have like a halo in 33 magnesium, this is a 7.5- orbit, you get like a peak at a certain energy where it's most likely to capture these 2 neutrons into this halo-like orbit. So you would like to see an enhanced cross-section there. And that would actually point us towards some origin of shell evolution because we know that 30 magnesium behaves different than it should be. It's one of these nuclei in the so-called island of inversion. Sorry, yeah? Yes, that is true, thank you. This calculation is for 1 neutron transfer. So we have extended that to 2 neutron transfer. The idea remains the same. What changes the cross-section here is the overlap, the matching of the incoming neutron with that orbit into which it's transferred. Just in 2 neutron transfer, you transfer 2 into those. But the idea remains the same, that the probability to transfer neutrons scales now with the beam energy. Okay. So we have done an experiment. You can probably tell it's going to be similar. We have still a recoiling proton to detect here. This experiment happened at CERN. Because of time, let me skip the details on how the beam is produced. So we needed a tritium target, which comes in a fancy bottle, and the tritium itself is contained in a foil. Unfortunately, this glass container broke, and we had 10 gigabecquerel of tritium, and we're not exactly sure where it was. But we figured it out eventually. It was a very stressful experiment. There's very stressful jobs, like being an American president. 4 years of presidency, right, changes you from this young-looking, ambitious man into something like this. But for a nuclear physicist, it sometimes behaves very much the same. So that was me before the experiment, and that was 10 days after we recovered the tritium and set up the experiment. You know how it goes, right? Nuclear physics experiments are tough. So, but finally, we made it work. This happened in September 2018. My new student, Tammy, just started to look into that. So I only have online quality. And I make it very simple. The idea is, if there is a state, which is like a halo state, then you would like to see an enhanced cross-section. And it was the excited 0+ state where people believe that is such a state. And indeed, that 0+2 state here, we expect it to be where the red line is. That's exactly where we see a lot of counts in our protons, right? So this indicates that we strongly populate 0+2. We hardly see anything of the ground state. Now, this is just a very small fraction of the statistics, but it points us already in the right direction, namely that the idea is right, that we see this enhanced 2 neutron transfer cross-section. So this was a little bit in a nutshell. There is more complicated physics involved, but with probing these shell structure key nuclei can tell us something about the origin of shell evolution and so on. Questions? This was a little bit fast and it's complicated, but I hope you get the idea. You can run them at 1 MeV per nucleon. You see already cross sections there. Beam intensity, sorry. I would say in the magnesium region, you need a few 10 to the 4. Yeah. This was with 2 times 10 to the 6. We had a good intensity here. Yeah. So the last topic is constraining neutron capture rates. Of course, that would be very nice to do. That's important for understanding our r-proce nucleosynthesis. Here's a sensitivity study for mum power. So the darker the green color, the more important the nucleus is. You again see how important shell structure is. This is tin 132. That's supposedly doubly magic, and we know it is doubly magic. So that's where it's important. And also here at the next r-proce peak in the mass 200 region, that's also where you want to measure. That's where FRIB, I think, will make a huge difference, because you guys can probably reach that, right? As well as this region. So what would be really phenomenal is to measure neutron capture rates there. You can measure that directly, but there have been methods developed to do that in an indirect way, but I think because of time, I will have to skip that. Just to tell you, the thing you have to measure, again, is the excitation energy of your nucleus, similar to how we did it before. And you also have to measure the gamma ray response. That somehow gives you, you remember that matrix I showed earlier of the 22 neon, where you have gamma ray energies and excitation energies? Once you have that information, you can put that into a model like the House of Feshbach and get the neutron capture rates in a model-dependent way, but you can constrain them that way. Okay, this is what you have to measure. Here's an example. It has been validated, so-called Oslo-method. Artemis is the specialist in that. If you have any questions, please to Artemis. So again, this is the same matrix here. This is gamma ray energy. This is excitation energy. You want to measure that. You put that in a model, and you get the neutron capture rate out. That was that in a nutshell. So how important is that? This is a sensitivity study here showing the known neutron capture, the known abundances from the r-proce here for the different mass regions. Here are the two prominent r-proce peaks. You see there is like an underestimate of the abundances from the measurements by like a factor of 10. And what has been done in this plot is the authors scaled the neutron capture rates by a factor of 10. That's the middle green line here. And the yellow-green band, that's when you scale the neutron capture rate by a factor of 100. So say if you assume you over or underestimate neutron capture rates by a factor of 100, then you actually can reproduce the known abundance distribution. Just we don't know what the neutron capture rate is, and a typical uncertainty is like a factor of 10, or maybe even up to a factor of 100. So Artemis and I just submitted actually a proposal at TRIUMF to measure that in the neutron-rich cesium region here. This is, again, a zoom into this mum power sensitivity study. We actually would like to measure down here, but we cannot do so yet. However, the idea is that once we have one measurement, we can do projections. There's like different models shown here. And the good thing is that if you look into their systematics, either they all underpredict or they all overpredict. So I think once you have shown which model is good in this region, you can make predictions. Maybe not in this entire region, but probably we can make some good predictions in this region of the nuclear chart just by doing one measurement. So that's a kind of the idea. And the thing we do that, oh yeah, these are the uncertainties actually calculated by Artemis. Here shown the cross-section in Barn for the neutron capture rate as a function of energy. That would correlate to the temperature in the neutron star. And you get like a factor of 10 here in uncertainty just by comparing different models in these calculations. So our goal in the measurement is to get that down to a factor of 2 or so. I think that's what we can do, right? The way we do that is very similar. We do, again, a 1 neutron transfer. You see I like 1 neutron transfer reactions. I like them because that's the closest you can get to the actual neutron capture. That's what the neutron capture is, right? You add 1 neutron to your seed nucleus. The DP reaction does the same thing. It's a different kind of reaction because the DP is like a direct nuclear reaction, and the N-gamma is like a capture reaction. But it's as close as you can get, I think. So in this case, we do not use 21 neon to 22 neon, but 142 cesium to 143 cesium. And then the idea is, again, the same. You get the excitation energy, you get the gamma rays, and then, as I mentioned, you can get the capture rates in this case. We just have to add some fancy equipment here called the MR recoil separator to indicate that the reaction actually took place in this case, but that's maybe a minor detail. So we submitted this proposal, and hopefully we get approved. However, as you've seen, that's actually not where we really want to measure. We, of course, would like to go into like below tin 132. So we have to upgrade something. We have to wait as for FRIB, but also the Canadian people have seen that we need better machines. So we are working on the ARIEL upgraded TRIUMF. That's going to be a machine which will not use the protons from the cyclotron to produce the beams, but will use a very powerful superconducting electron linac to induce a photofission. And that gives certain yields around tin 132, which can be very competitive and very well suited for these kind of experiments. So the good news is that the first update of that is a new ion source, which will go hopefully online this year. This will be already a major upgrade for our experiments. So do I have another 5 minutes? Okay. So this Oslo method, as I said, is you need gamma ray energies and excitation energies. Now, we're always limited by these thin target foils, unfortunately. So usually we use something like 160 microgram per square centimeter CD2. That's the thickest you can do for these kind of DP experiments. If you go thicker, then you run into issues with the resolution of your experiment. Now, if you only have like 1,000 particles per second or something for something exotic in the r-proce that you want to study, you can't do that experiment even in 5 days because you don't see any peaks or anything appearing in that matrix. It's just not enough statistics. So you think, okay, I'm clever. I just make my target thicker. But then the problem is because of the scattering here in the foil of the beam and also of the protons, you cannot reconstruct your energies anymore. That missing mass spectroscopy, that nice understanding the kinematics I told you of, that doesn't work anymore because you don't understand it anymore. You don't exactly understand what happens in that thick target. So yeah, we do still measure gamma ray energies, but we cannot associate any excitation energies. They're just like vertical lines. So in order to improve that, we came up with the idea to replace the CD2 foil with just an extended D2 gas volume. So the simple idea is this: the incoming beam, something heavy, goes into the deuterated gas volume, and then you undergo a DP reaction, so that proton flies off here, or it may fly off here. And now imagine that you have a tracker, then you could actually reconstruct where that has happened, right? So you measure the proton impact here and here, you draw a line, and then you say, okay, that must have been somewhere here. And that would now allow you again to reconstruct everything because you know what the energy was at which the reaction took place. So this tracker, I will skip these details. This is the mechanical design stage. We call that TI-STAR. It's standing for TIGRESS Silicon Tracker Array. The mechanical design comes from a colleague of mine at Colorado School of Mines, and TRIUMF is also participating in this project. So basically, the idea is we have a gas volume here, which is surrounded by multiple layers of silicon detectors. For the experts here, the silicon detectors will be read out by ASIC chips. So these are specially designed, computer chips, you can say, which are doing the exact purpose of pre-amplifying the signal and also multiplexing it and everything. We need to do that because we only have 20 centimeters of space. We did that earlier. That's not yet the TI-STAR detector, but it can be used, or we will use it as like something to start with. This we built for Riken in Japan. This is an 8 by 5 centimeter large silicon with 100 micrometer fine strips. So this detector has 800 channels, and they go here to these little ASICs, which take care about signal amplification and so on. So we think we have a good prototype for something we can also later use in TI-STAR. So this is how the individual detector layers will look like. You have the silicon layer surrounded by these ASICs at the side. And we're going to use the so-called Skyrock ASIC, which is a new ASIC which comes from France. So those are the people working on that. We just hired a new postdoc, Hadi, and Leila Attar. She worked on the GL4 simulation. This is the current mechanical design of this. You see again here the gas target, which is like contained by a vacuum foil here. And we got the budget funded to 75%. I'm still waiting for Ontario to cash into this device. And then we'll hopefully gain a lot. You have a question? Okay. So we have in total, sorry, I was too quick because of time. Sorry, I misjudged this. This is a simple sketch. There will be 3 layers in total. We need 2 layers to get the position, like here, right? You need 2 layers with fine pitch detectors to get the position. And then we need a 3rd layer, that's the thicker layer, to get the total energy that has been asked before. Right? How thick is a detector? All right, how do you stop the beam? This will be a 2 millimeter silicon detector stopping the protons. Yes, so what is the benefit of that? Now, if we now throw in 1.9 milligram D2 gas, that corresponds to actually 8 milligram per square centimeter CD2, because CD2 mostly consists of carbon and not of deuterons. So that's even more statistics than here, but still now you're able to see the individual excitation energies with a resolution of about 200 to 300 kV, which is good enough for this Oslo-method. So you can really gain, in comparison to 40 milligrams D2 here, to almost 2 milligram, 40 microgram to 2 milligram, something like a factor of 50 that you gain in luminosity by building such a device for this specific purpose. So this is what we are trying to do. And again, the idea of TI-STAR is you remove the foil, you have an extended gas target, and then you can track where in the gas the reaction takes place. And then you can make this target much, much thicker, and you can still do the experiment. So this is the hope. Okay, I think this is everything I wanted to say. Let me go through the main slides. I skipped this time. It was a bit ambitious, but you never know how it goes, right? And this is my team at mostly at the University of Guelph, and my former student from Munich. And yeah, thank you for your attention, and I hope there's more questions. So the TI-STAR was a bit quick. Yes. Or was it so quick that it... timeline, I think that we have a well-advanced prototype in 2 years from now. Yeah, it's about the timeline. It's a complex device. But the engineering effort is high. It's difficult to squeeze everything into 20 centimeters with the gas volume and things. But we have near final drawings from the people working at TRIUMF. So I'm confident that about 2 years is a reasonable timescale. We had such a good start. There was many questions also from the students. That was good. Thank you for that. Another student. Yeah. Yes, that's true. You totally can do direct measurements with EMMA. EMMA is located, though, at ISAC 2. So you typically have beyond 5 MeV per nucleon. That's usually too high for a nuclear astrophysics direct reaction rate. If you transfer that to center of mass, that's usually way above any normal temperature. And also, EMMA is not designed for, yeah, it's not designed, say, in a P gamma reaction. I'm not sure how good EMMA would do. Yeah. Right. Yeah, so for those cases, it might be possible, or then you have to extrapolate towards the temperatures that you're actually interested in. No, both those can be used, just reuse it in the right. Yeah, sure. Yeah, that depends on the condition of the star. It basically ranges from the lowest to the highest temperatures. I really had too many slides. Eh? And neon 22. Oh no, where was it? Here you go. So in AGB stars, it's mostly up to 250 gigakelvin. If you go into the S process more, the higher temperatures are relevant. Yeah. Not for 5. You mean directly? I don't think there's any direct measurements for any of those. Those could be measured depending on the spin. If it turns out to be a 2+, then the cross section could be high enough. If unfortunately it's a 4+, then you're again 3 orders of magnitude too low. I don't think there has been a direct measurement on that one, but I'm not 100% sure on that. Yes. Right. Right.
I'm wondering, since you're above the alpha cluster collector, if there are any structure contributions, there would be such specific structures. Because in the end, what you have is a model.
Sure. Absolutely.
I'm wondering if they change cluster.
To be honest, I'm not able to exactly answer your question. I know that the largest contribution so far is from the spin. So once you remove that, something else will dominate it. It could well be structure. Those states, though, have been populated. No, they have not been. They have been populated in similar. No, actually, I'm not sure. I'm not 100% sure about your question. But yeah, for. Oh, okay. You mean, okay. But keep in mind, the level density is really high, right? And it's between 8 and 11 MeV. There's like 30, 40 nuclei. So to claim something like that, but yeah, maybe. That is true. Yes, yes. Could well be. Ah, okay, that's good. I'm around all day, so.
I think there are no more questions. Let's thank Vince again.
Thank you very much.